So 3D user interfaces. These are very popular, right? I mean, this is from Iron Man 2, and that's how we want our 3D user interfaces to be, right? If you look at this, I see this clip every time, and I'm going like, wow, I really want my user interface to work like this. You know, he snips the fingers, the thing rotates, and yeah, that's so pretty. What I want most in this video clip is actually the display system, because if you think about what that display really can do, is can display something glowing in space right here in front of us. There doesn't seem to be any projectors around or so on, okay. And it's bright and everything, and it's great display, and in a second you'll see the most magical feature of this display system that I don't really know how to do. And that's really how you want it to do. And if you listen to what he says, he has this AI where he gives commands and his gestures, and it just all works magically, right? And if you have done any user interface development, this is a dream. This is clearly a dream that is really hard to achieve, right? And there's a lot of magic happening here. Right? And my favorite part of this movie, you know, this gesture here. Oh, yep. So, awesome display system all around him, and worse yet, and he had to film all of this without the display existing. That's the magic here, right? I mean, none of this existed when he was filming it. But the most magical aspect of this display system comes now. So the light actually comes out between his hands. So how is that possible? There's light, his hands are closed like this, and there's light coming out between his hands. So where's that light coming from? That's a question where, you know, I go to my physics colleagues and they go like, don't know. Don't really know how to do that. So, but that's the display technology. That's the fun part. But if you have watched this movie, or you go watch it again, watch it what the user interface does, how everything just works. Not quite what we do in real world, right? I mean, today, if we talk about 3D user interfaces, we often have big screen displays, so you have some big display here and you see some 3D data, or you do computer-aided design here, right? Or you do 3D desktop managers or 3D window managers, or whatever you want to call them. Sun's Looking Glass, a prime example here. There have been hundreds of proposals of this type, and I know 0 which have succeeded in any way. One of the issues is that the readability, for example, suffers greatly. So you actually don't have much information density in terms of content, which is one of the issues why this is not so great to use. One of the funny things about Sun's Looking Glass is music comes on CDs. Oh, no, wait. Not anymore, right? 3D user interfaces in games, and there's lots of examples of the Electronic Arts Spore, the game that had a very interesting user interface for 3D creation, and one of the more expressive user interfaces for 3D creation. Even kids my kids, when they were young, were able to create some content there very quickly. And that's very interesting. So much beyond what you would typically have, say, in a first-person shooter and so on. Then something I'm not going to talk much about is medical and volumetric visualization. Talking about the insides of things, I'll mostly talk about surface-based computer-aided design. And then, of course, we have virtual reality, right? And in this case, old-style virtual reality with CRTs up here and mirrors and a box full of tracking equipment. Today, this all looks much better. But I just put it up here to remind people where we were not so long ago. So one of the things that I've done is I've looked fairly closely at the various technologies that we have and what these various technologies allow us to do and what they don't allow us to do, and the limitations that they impose on us. So one of the things that you notice when you deal with virtual reality, you want to have stereo display, right? Because then you get depth perception, you have a better perception of 3D. So we have various 3D technologies such as the typical stereo glasses where we do linear polarization or circular polarization or something like that. Or we just have 2 display panels in front of people's eyes. That's pretty standard stuff. One of the things that this costs you is that collaboration goes down the drain. Why? you take polarized filters in front of your eyes, and you have somebody else across you who has also polarized filters in front of their eyes, you can't see their eyes. So when you talk with another person, where do you look at? Eyes. Exactly, right? So that personal communication suffers immediately. Right? Now, if you're task focused, that's a different story. But if you're negotiating about $1 million, I want to see the guy's eyes, right? My partner's eyes, right? Because every twitch matters. Every twitch is $100,000, right? Think of it this way. Right? So it really depends what you want to do. Then we have various autostereoscopic displays. So this is a classic autostereoscopic display advertisement. And it suffers again from this little problem. So how does this tiger jump out of the screen? How does that work again? That would mean if I hold the display like this, the tiger is displayed here, the light would go out of the screen in midair, do a 90-degree turn, and go towards my eyes. And magic happens, right? Physics people love that, right? We don't know how to do that. Quantum physics? No. Still not there. So I just love these marketing images. So typically, the correct answer is really, this is the display, right? This is really what you get, right? So I played a little bit with autostereoscopic tablets, and that was not so pretty. We can have holographic displays. This is basically a rotating disk where you project images on, and this will allow you to display things floating in space, typically transparent dots or transparent content. Very interesting technology-wise. One of the problems is that you have transparent things floating in space, and we think that we can see more that way. Many people think that we can see more that way, and if you actually test it, you discover, well, if you think about it real, forget about all the display technologies for a second. If you take transparent layers, like print out foil transparencies, old ones, and you print multiple layers of them, and then you try reading anything on the 5th layer, then you see where the problems are with this technology. Okay? Regardless of what the technology can do, multiple transparent layers is not something that we're really well, it's not a task that we do well. Okay? Yes, you can have a glass surface of a table and you can read something underneath, even if that's transparent, and maybe the 3rd layer. Okay? But it ends very quickly with transparent layers. There's nothing that can display solid surfaces with such technologies at the moment. Okay? That's a bit of a limitation of this technology. Then we have the little problem that our human vision is like this. It's wide, right? I can see my hands out here. Okay? Most VR devices are like this. HoloLens, just to make it clear, 40-degree field of view, that's like this. So if people tell me, we want to use a head-mounted display with 40 degrees field of view to study navigation, how we move around in the real world, you have the problem that to walk parallel to this wall, I have to keep this wall in my field of view. Okay? Now, if I have blinders, it's a really easy task at that point, right? Not, right? It's getting better, I have to say. Rift and all of these technologies are finally getting to wider field of views, and that is much, much better than what we have. But we're not quite there yet. Let's call it that. And then we have perspective. So can somebody tell me if the right text is on the top of this block? No, you can't. Not enough pixels, even though it's an HDMI display. The problem with perspective is that, and I don't have a page of paper. Can I borrow one of the pages of paper from this? Yeah, any page that I can use without breaking any secrets here for a second. I'll just use this here, okay? I don't need to show you what's on it, but reading this page like this is easy, right? Reading the page like this, not so much, right? Remember that in a galaxy far, far away, the top of the page, you can't read so much, right? If you put it this way, you can't read the bottom of the page. If you put it this way, you can't read the right side of the page. You can only read half the content, half the sentences, right? Or half the words, right? This way. So the only sense that makes sense is really this way, and you see this. Thank you very much. The way you see this in many 3D user interfaces, people try with rotated text and then typically end up with text facing the user, because that's the best way to read the text. Right? Then we have some human limitations that are worthwhile to discuss. So one of the first ones I want to highlight is, so how many of you have training to actually fly in 6 degrees of freedom, in all, in forward, backward, left, right, up, down, right, and all rotations, right? How many have the training? Well, in our dreams, we do. In our dreams, we do it, no problem. Okay, I dream about it all day too. If you actually look at what people who really do 6 degree of freedom tasks have amounts of training, it's like astronauts, fighter pilots, night divers. Every one of those professions has hundreds and thousands of hours of training before you get to do the fun stuff, right? Before you're allowed to fly the fighter jet upside down, you better have some serious training. And if you talk to the people in flight school who get who get to say who gets to fly upside down and not, well, they say, yeah, the first time they do it, they basically have the trucks on standby because it's so easy to make a mistake. Right? So when we build stuff in the real world, we typically build things like scaffolding. We don't build things in 3D. Michelangelo did not go there, take the chisel and hammer it out of the block of marble in free space. No. There were support structures to stabilize hands, to make it sure that that priceless piece of marble wasn't damaged, right? More than it needed to be to have the David come out of it, right? So I don't actually know where north is here. Let me figure that out for a second. I think somewhere about there. Is that about right? Okay. So would please everybody point to Europe. Okay, most of you are pointing horizontal. I disagree completely. Yeah, the earth is round. Yes. Little problem. Of course, I completely set you up. I showed you a flat map, okay? My fault, all right? But the point that I'm trying to make is we all think in 3D, yet a lot of our functional, what we do in everyday practice is not really 3D, okay? Building plans are 2D mostly, right, and all of that. So, okay. Then we have perceptual issues. This is our perceptual system showing us the old guy looking smaller than the young guy. Well, of course, in this case, it's an optical illusion. It's a room that's built crooked, right? So it's actually fairly easy to fool the visual system. Point that out. Then, in case you were wondering about this image, this is a guy hanging upside down to work on a pipe. This is his head. Interest trying to get in there. The real world profession that I use to explain this is a plumber. Have you ever seen the contortions a plumber goes to actually work? Why we want to see our hands when we work. If you want to do anything with precision, you want to see your hands. This is very strongly hardwired, because why would otherwise the plumber, okay, if I do a task for a minute, if I'm working on a chain and I'm putting that screw in there, I'm not going to look anymore, right? But for the first time, okay, I'm going to look at that screw, right? So we actually are really biased towards working with where our hands are visible, also to achieve the precision. Okay? If we're doing a task, again, for the millionth time, that's a different story. Right? But if you're doing tasks that you haven't done many times before, then you actually look what you're doing. And then, last but not least, we also have a little problem with our input devices. So I put a pen there as a typical input device because it illustrates the point quite nicely. So I give you a pen. Please tie your shoelaces. Okay, I give you 2 pens. Please tie your shoelaces. Our hands are so much more powerful interaction devices compared to any technology that we have. Okay? Our hands are so much more versatile in terms of what they can do relative to the input devices that we have, which are basically limited to the tip. Right? Because it's not even as if you interact with anything here, back of the pen. It's really the tip of the pen that matters on the computer. Right? It's a 2D input position or a 3D input position. It doesn't matter. Please tie your shoelaces. Right? So, I've been doing various projects in this aspect. This is one of Rob's early systems. So here's the one slide that I'll be talking about Rob's work. He basically spent his PhD, summarizing your PhD very brutally, to investigate how we point in 3D. and how we can have fairly accurate performance measures, how we can characterize 3D pointing performance, both for pointing with the tip of a pen or with basically like a laser pointer. Okay? And what Rob did is he basically took a 2D paradigm for investigating pointing performance in 2D, the ISO 92419 standard, with a good measure of throughput, which takes speed and errors into one number, so that you can compare somebody who's fast and sloppy with somebody who's slow and more accurate on a reasonably equal basis. And you take that into one, and that gives you the throughput measure. And he took that 2D throughput measure and generalized it to 3D. And so you have these Fitts law circles, so you would point at each one of those targets either by tap, 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 tap. So the interesting part about why I showed the oldest system is because one of the experiments we did was literally tapping on the surface of the display, which is a 2D task. And then we went up into 3D, so we were able to see the drop in throughput and to verify that it actually dropped performance. And sorry, that was your PhD.
One slide?
Well, we built in many different aspects on this, so this is, you gave a job talk here, so it's really, shouldn't expound on this much more than I need to. So we took this in many different directions. So together with Gerd Bruder and Frank Steinecke from Germany, we took this, also tried this on a large multi-touch table with stereo display, as you can see here, where we looked at how this works with a finger, right? And found roughly the same things. Again, typical setup here, right? These stereo glasses, you have some tracking system, you will have some marker on your finger, you can see the retroreflective sphere right there, and so on. The typical technologies to try this. So what we did here we actually looked at how this, so this is up from the surface of the display, so this is the display, this goes up, okay? And this is performance basically, right? And so you can see as you get higher, performance drops, okay? And so we actually did two things. We compared 2D touch selection, where you press through to the target, and 3D selection, where you have to actually have the, so you actually touch, in the 2D condition, you actually touch the surface of the screen, whereas in the 3D selection, you have it hold in the air and you click with the other hand, right? And for consistency, we did that also, to click with the other hand on the touch the screen selection, and you really get this nice crossover effect that as long as you're within about 10 centimeters above the screen, touching the screen is better. So that's why the green curve is higher here, right? Up to about, we guess, about 8 centimeters, somewhere around here. And then the higher you go, the bigger the stereo conflict, and then it's actually better to touch in 3D. Right? We explored this, and this was published at SUI in 2013. Now, you have all heard about input devices such as the leap motion. So the leap motion is a little input device that allows you basically to hold your hand in the free air and use it to point at the screen or do some interactions with this. We wanted to know how well does it work as an input device. So our first evaluation of the leap motion, and this is together with Michelle Brown, we came to the conclusion that we had about 3 bits per second if you use it to point at the screen. So this basically, right? So there's interesting questions came up, you know, is the elbow stabilized or not? Does that affect pointing? No, it doesn't, as far as I can tell, okay? So it didn't matter if you stabilize the elbow or not. Basically, this is 3 bits per second, instead of the mouse, which is traditionally roughly around 4 bits per second, okay? Interestingly enough, when we played around with the system, we discovered that the leap motion actually has support for tracking rigid objects, long rigid objects, such as a chopstick. So we measured the performance with a chopstick, and with a chopstick we got 3.89 bits per second. This is the best input device for free air pointing that I know. In other words, this is the best input device for 3D input that I know at the moment. One of the issues is that the leap motion can track it very well. And one of the functional and actually more human issues is that if you think about it, how you hold a pen and how you point with it, you stabilize the pen with multiple fingers. And you're using one finger to push and the other one to stabilize against, or to control the forces against, and that actually affords you quite a lot of precision. And upon reflection, I went like, oh, that's obvious. In hindsight, it's obvious. Handwriting, if you look at how accurately you can control the tip of a pen during handwriting, now you understand why this is such a good choice. Okay? So again, this was only a 2D task in a sense, right? You only point the joystick at the screen, cursor shows up there, and you get the cursor into the target, right? So this is really only a 2D task. It's not really a 3D task. But it allows us to compare, input devices very accurately. Now, we did go into 3D. So this is together with Vanessa Wiebert and Jeremy Copperstock from McGill. We did go in 3D. We compared 4 conditions where we had something like we call this an air pen or chopstick-like interface, a real chair, a mini chair, the typical 3D tracking solution where we have markers on the hands and on the fingertips to discover where the fingertips are, so we can discover a pinch, and also discover the orientation of the hand, the position of the hand very precisely, with a known input device, a phantom haptics device, which we used only as input device here, okay? And so the task is the following: you grab this chair and you put it basically in the target position, right? So you take this chair here and you put it here, right? In that position and orientation. And so we investigated basically how long does it take to do this with these 4 input conditions to do this task, this 3D docking task as it's known. Okay? And the results are interesting. So you first come into the issue that you need to think about a little bit about the mappings because, for example, with the air pen, you have the rotation of the pen and the movement of the pen, and you want to keep that in the tracking area and so on. So there's little issues around exactly how you map the interaction, but I don't really want to talk about that. What we found was that in terms of accuracy, this is the best input device. No surprise there, it's a mechanical tracked system. You can track this better than anything else. But what it also tells us, it's most probably the tracking position, the tracking accuracy that actually limits this to some degree. Though, I have to say, this one provides you a bit of friction, and so actually that helps you stabilize your hand. I don't have an answer to this question, okay? But that's one thing that I would love to know. If I have a frictionless system, which is hard to do, how does that change that? But in terms of performance, these 2 were the best. Now, if you look into the literature, what should be the best, you will find that the mini chair is the one thing that actually stands out because it's actually a replica of the chair. But we found that this one not significantly different in terms of performance. I hope I don't block your view too much. Tell me if I do, okay? So they were not significantly different. Moreover, in terms of preferences, everybody liked this input device. So for me now, I'm going like, is there something with pen-like devices in 3D that actually is superior to other solutions? Yes?
Sorry, I missed something.
Sure.
What was the task here?
Again, put this virtual chair into this position. So you have to move it and rotate it, okay? So again, I have to put this pen into this position, right? Or this pen into this position, it doesn't really matter. Right? So it's a docking task in the sense that you actually have to get both the position as well as the orientation correct, okay? 3D position and 3D orientation. Also, unsurprisingly, and this is a little side note, most of the time is not spent in translation, it's spent in the rotation. 3D rotation is clearly the harder task. But that's not a surprise. All right, so based on all of this, and based on a lot of thinking around this topic and analysis, what actually makes sense, we've come up with a set of guidelines how to make 3D user interfaces more usable. And the first version of this I did together with Chad Wingrave. I presented that at Dutch Tool Seminar in 2008, and then there's a subsequent version which I did with Rob. But here's a set of guidelines. Well, the first thing is no floating objects, because look around you. How many objects float in this room? Okay, temporarily, sure. Right? Okay, but how many objects float in this room, in this city? Okay, but I hear the helicopter there. Okay, but that's the exception of the rule. Everything else is attached to the ceiling, to the wall, or stands on the ground. So somebody tell me why in computer-aided design systems everything floats by default? Yeah, but I'll ask it this way. Do you think that human perception is not biased by, you grew up and floating objects are clearly the exception in your life, right? Everything you see, everything you do, everything is attached to something else.
But then there's novelty with anything you see on screen.
I agree.
Everything is okay when you see it on screen just because of how the movies operate and how they, conditioned us to accept whatever they give us.
Sure, but in terms of manipulation, if you interact with things, right? Movies are interesting in the sense that you see them, but you don't allow to play with them. Right?
So it is frustrating when things float in space.
Well, it's actually interesting, right? Watch a kid play with soap bubbles. First thing they discover is, oh, it's not quite as easy to tell where they are in space. So, I recommend, unless you really need it, unless you really need it, don't have the default in your user interface be that everything floats. Then we have cars that do collision avoidance, right? In virtual reality systems, it's normal that I can just walk through the closed door, right? In fact, you can easily walk through walls, right? That's nice, but also very disorienting, as people in game community know. If you are into a situation that you can kind of get in between the walls, most novices get completely disoriented and don't know how to get back. So, even for the viewer, right? And for objects too, right? If I want this pen to be inside the table, I pull out the drill, right? Right? I'm not going to do that here to this table. But that's again, it's an exception mechanism, it's not the rule, right? The default is that things don't interpenetrate with each other, right? It's not as if I can take this pen and put it into my hand. Ouch. Things don't break. Well, things do break in the reality, and that's one of the inconveniences of reality, right? I'm not going to do it, don't worry. If I drop this glass, it will shatter, right? If I drop this pen, it will roll under the table, and I have to dig it out, and I have to bend down and get it up. That's one of the things that I don't like so much about reality. We do want to see our hands, so why do we have a need to actually regularly manipulate things that are not visible? Do I need to design my user interface for things that are not visible? No, if I really want to manipulate it, I can bend up, I can navigate here and do this. So I don't necessarily need to define my user interface so that I can manipulate it as if I can manipulate everything. It's easier to do only the things that are visible. One of the consequences of that is, if you think about that, everything that's visible is like a 2D screenshot, maybe 3D if you have stereo. But it's basically 2 images full of information at most. It actually reduces the problem significantly. Do we really need stereo? Perspective and occlusion are actually the strongest cues. Well, there's some debate in exactly which distance you can dog and motion cues and so on. But I'm making a very big simplification here, I'm aware of it. But perspective and occlusion are really strong cues for 3D position. How do I know this? Even one-eyed people are allowed to drive. Okay, if there was something important about stereo vision in the driving task, they wouldn't be allowed to drive. Okay? Very simple. Rob's work, sorry, I need to sneak in some more, but just my sort of work here. Lag doesn't help with interaction. And today the community recognizes this. I mean, the Leap Motion blog has a nice article, two-part post about why lag matters for them and why it's so important for them, and how do you reduce it in the system to actually make interaction more performant and enjoyable and all of this, right? If you have a lot of, you move your hand and then the virtual object moves, that kind of doesn't translate so well. It also has bad, as Rob showed, bad impacts on performance, and accuracy suffers and all of these things. I will talk about this point in a second in more depth, but I want to point out that we're really, really, really focused on having a single point of interaction in most of our design. When you manipulate an object with a computer, you think about the cursor. And I think that's wrong. If I have the cursor on this object, technically this cursor is over the back surface of this one here. And most systems that I know will map, because the cursor is over this surface, will put it in the back, in the second surface here, not in front. If you look at how perception works, and there's studies that have done with animals where they've looked at which parts of the brain light up, which part of the visual perception areas light up when they manipulate an object. You find interesting facts such as that if you have a pen, if you have some instruments in your head, the perception is actually for the whole area of the pen, in fact, part of the hand too. So it's actually the area of the object that is attended to, not a single point. Even if they're only using the tip, of the object. And I have a technique that uses this fact to good advantage in a couple of seconds. Lots of constraints in real world, like you have a wheel that goes around an axle, right? And so you use those. That's a simple guideline, but if you constrain things to, say, stay on the surface or rotate around the joint, makes manipulation easier. Not very surprising, but still to be said. There's nothing wrong with having some 2D scaffolding to construct 3D. We do that in real life. And you will see that most 3D systems, computer-aided design systems, allow some form of, okay, you can put a construction plane this way and construct things easier this way. You will see that in many ways, and that makes things a lot easier. And then last but not least, navigation in 3D. You also don't want to fly all 6 degrees of freedom. The first degree of navigation that everybody takes away is that you don't rotate your head, because that also makes it possible to fly upside down. There's a single game that I know about that has full 3D navigation that was commercially successful, that allowed flying upside down and everything. 1995. Descent. Wow, somebody knows it. Awesome. I'm impressed. Rob knew it, but awesome. So Descent is a game where you can literally fly all 6 degrees of freedom, and it's the only game that ever achieved any commercial success. Since then, pretty much all games are 4.5D mostly, because typically the third degree of freedom in translation is crouch and jump, and that's it. There's no real more control than this. Okay. All right. So based on these guidelines, we've created a couple of systems that allow us to take some of this into 3D and actually use them to manipulate. So this is the Jiang O's work that was done about 10 years ago now. This is a system that allows you to slide objects based on the area of what's visible behind the object, and uses the whole area of the object. And so you can take these parts here, and you can slide them, and basically they stay automatically in contact with everything behind it, and it makes a task of assembling this launch here fairly easy. Now, if you try to do the same thing with, say, any other system, you will spend a lot more time with it, and we tried that in an experiment, and yes, it showed it. And you can see that sometimes there's multiple solutions, so you see this frame popping forward and backward. But other than that, it's a fairly easy task. It's one of those experiments where the real metric is the number of unprintable words per minute. I can't report that scientifically, but I can state, in the other conditions that we tested, the number of unprintable words per minute was much higher. So this was the best condition. So the fundamental technology behind this is that we actually literally use the graphics cards to look at what's behind the objects. We actually look at images such as this, which are completely nonsensical because they show the backs, what's behind the back faces of the object. So you don't understand really unless you think hard about, because you never see that in real life, right? You can't see through objects. So we are using then the distances between the objects to actually discover when to snap, where to snap the object, and we're using basically the minimum overhaul, the whole area of the object. And because that's a lot of computation, we do that all in the graphics card, and in the first generations we did that in very naive ways. Today we do that shaders. I'll talk about a much more refined version of this in a minute. We also look for collisions so that we don't have objects interpenetrate with each other. So this is all fairly straightforward from a computational point of view, though very intensive because there's a lot of pixels. So with this, we have created some systems such as a puzzle system that's Dimitri showing off here, which is basically allows you to slide objects and they stay always in contact, and even during the rotation, so you can see they bob up and down to actually stay in contact. And so here is a puzzle task. This is not real time, this is sped up by a factor of 2. But this, as far as I know, is the fastest system to do a puzzle in virtual reality. It uses only a mouse here in this case as input device, but you could map that to a leaf motion or touch screen or anything like that. Very easy. Okay. There's a little bug in the system that with the collision detection, because we do use collision detection, that we have to pull this part out here to actually get the other part in, and that's an artifact here, but it shows you that even with such things, it works fairly well. Now that the sobering thought here is, we did this and said, great, this looks awesome, and then we gave the same task in physical reality, as in with wood pieces. It takes half the time. Even with one hand. That's sobering. One of the issues is indeed, again, this issue that your hand can manipulate an object in so much more rich ways than what you can do with, say, a mouse. Okay? That's one of the issues, but it's not the only issue. Actually, you know what? I'll show this one in a second. So this is actually unpublished work now, and I most probably have to start this video because I haven't linked it yet to play automatically. This is stuff that's currently submitted. This is the same sliding paradigm. This is Junwei Sun, based on some work that Dimitri Shorodov did previously. Same idea, sliding method. And that always ensures that the object is visible, so it will, it would become invisible, it gets popped to the front, so you never drop it. And a new method here that allows us to now hit the shift key and slide the object basically in 3D. So now this is a sliding method that allows us to slide objects in 3D, and we did, of course, the use and relative to any other object, so you can see it sliding off the wall here. And as soon as it collides, it gets back into sliding mode. And we did the user study on this, and everybody loves it. And performance times are better. Sorry, I'm glossing over a lot of things here, but you can also push objects down into floors or here into the wall. The same thing is just shift, but just move into the object instead of out of the object. It just depends on the mouse direction. Makes it very easy to do many different tasks. And so it's just above the table, and as soon as you pull it a little down, then it will pop in there. So you can do this even because we accelerate this. So I don't know if you can see this, but there's lots of little point clouds from a laser scanner floating in the air, and we can slide even on a point cloud. Because we do this all in the graphics hardware, so we can do very complex computations by accelerating them directly. And then you can even slide relative to that point cloud. But that's work that's currently submitted with some further enhancements. But that's what I can show publicly at the moment. Talking about 3D rotations, here is an attempt to make 3D rotations a little simpler. This is now touchscreen. This is actually filmed off the tablet, and I apologize that the video is a little fuzzy because this, but it's the only surviving video of this. So this basically maps the third degree of freedom to a second finger. As you can see the gesture here, and that's why we show it as a live video to show that direct interaction on the touchscreen here. This is running on an Android tablet. You can see the Android icons down there if you were really interested. This runs in real time, even on an Android tablet. If we want to be able to move objects and rotate them at the same time, we map sliding to one finger. So this is again the sliding paradigm here. And with two fingers, we go into rotation mode. Fingers down, and then now you can use the third finger for the third degree of rotation. Right? So basically, the screwing motion. Right? So you can either use your ring finger, which feels a little awkward at first, but there's a good application. We'll show that in a second. Or your thumb. Either we just take any third finger as the rotation for this. this is Doug Scheuwig, this is part of this master. But much simpler than that, we just do tap, tap, and the object rotates to the position and orientation that's implied by this. So, yeah, and if you're on the edge of the screen, you can use your ring finger. That's the nice part about using the ring finger. So just one. So here, this takes the base of the chair and matches it in orientation without having a collision. So you can see tap, tap. You can always rotate the object and translate it at the same time, the back of the chair onto the ground, but while still avoiding collisions. You had a question, sorry.
So, I like this way of interacting with 3D objects on the screen because my challenge with 3D interaction in general is fatigue. I don't think you can hold, and of course accuracy.
The gorilla arm syndrome, yes.
Yeah, and of course accuracy
Yep.
as well with
Yep.
fatigue.
Absolutely.
So like as you know, like when you rest your fingers, hand, arm, whatever against something, then you're giving it something to lean on and to you know.
Provide a little bit of friction so that you can afford more accuracy. I completely agree with you.
So yeah, I like that a lot.
Thank you. This is something that I've been thinking about a lot. This kind of shows through a little bit here, because there's this trade-off, right? And so what we found also with the Phantom, even that little bit of friction that's actually in the system seems to provide more accuracy. I can't prove that comprehensively at this point in time, but I can just point to it. Okay, then we went into, this is together with Mike Ortega from Doug Scheuwig, Mike Ortega from Grenoble. This is a paper that appeared at WIST last year. Sorry, I haven't linked them yet to play automatically. This is a new method for navigating around objects. So this is now object-centric rotating around an object method that has the property that it stays at a constant distance to the object. So if this is previous work here, where you basically have weird artifacts like this bobbing motion here, because it's based on the geometry of the object. We have one of the contributions that we have that we smooth the path in a much better way. But it's not just smoothing the path; it's actually computing it and smoothing it in a way that actually doesn't get in the way of interaction. Right? And so with previous work, you have these points where the camera completely comes to a stop and only rotates. So you have a lot of change in optical flow, and optical flow has been correlated to motion sickness and also decreased interaction performance. So we also have here the methods that we can navigate around objects, but if we're close enough, the camera will basically squeeze between the objects. And if it's large enough, the group, it will automatically rotate around the whole group. So we actually look at what's visible on the screen and decide, do we rotate around the whole group? So if you say far away from a group of objects, you will rotate around the whole group of objects instead of rotating around one object in the group, right? Without the user having to say, oh, I want to navigate around the group. It just automatically. And so we can map that to interaction on the touch screen here. And so there's technical details that I'm not going to go into here, how we actually compute this. There's interesting problems here because you have to switch from interpolation in one direction to interpolation in the other direction in a seamless way. And so there's lots of little details there that make that interesting and technically challenging. So I'm not going to go into depth here. Oh, thank you. But you can see that this is actually running on a large touch table at this point. Here's another example case where we navigate around a fairly complex geometry interacting directly. Something else, I will be actually going to Toronto on Thursday. My last master student there, Domi Papoy, is defending there. There we have been working with camera speed control techniques. So this is a touchscreen again, and this is navigating through a very large data set. The speed is automatically determined here. The user only gives direction control. So you can flop. This system slows you down in the presence of geometry in a way that allows you to navigate through fine cracks, and then the camera will speed up. Now I have to say this is an older version of this system. We're working on a refined version where there's some abrupt changes in speed here. but it makes it possible to fly to very distant places fairly quickly, and then slow down again and get, even into fine cracks. But this is basically the idea that you can use the geometry to determine the speed. This idea has been tried previously.